Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, sorry because just now I had a line connection problem, internet connection problem. So this is the continuation from the previous video on the emitter bias configuration. Okay, so in the last video, I stopped at this slide. Okay, so I already explained on the emitter bias configuration. Okay, so the difference between the emitter bias configuration is that it has an additional resistor RE here, okay, at the emitter. Okay, so this RE is used to stabilizes the bias circuit. Okay, so so I want to do the voltage and current analysis. Okay, so basically the step is the same as the other configuration. To solve for the analysis, you just need to use the Kirchhoff voltage law, KVL. Okay, so from the graph, from the circuit, this circuit, okay, basically you have two loops. Okay, so if you redraw this loop, the first loop here, we call as the base emitter loop. Okay, so because this is the base, this is the emitter, so that's why we call as the base emitter loop. So when you do Kirchhoff voltage law for this loop, you will get this equation where VCC equals to negative IBRB minus VBE minus IERE equals to 0. Okay, and you know that, remember, for this configuration, okay, the current direction is like this. Okay, so you know that IE is equals to IC plus IB, and you know that the collector current is equals to beta IB. Okay, so you know that IC is equals to beta IB. So you will get beta IB equals plus IB equals to beta plus 1 multiplied with IB. Okay, so IE for this circuit is beta plus 1 multiplied with IB. Okay, so then you put this equation into the previous equation, this equation, you will get this. Okay, so you will get VCC minus IBRB minus VBE minus beta plus 1 IBRE is equals to 0. Okay, and then from this equation, okay, you can solve for IB, and you will get IB is equals to VCC minus VBE divided by RB plus beta plus 1 multiplied with RE. The second loop, okay, based on the emitter bias configuration circuit, we have a second loop, which is the collector emitter loop. This is collector, this is emitter. So that's why we call as the collector emitter loop. So if you do the Kirchhoff voltage law over here, you will get IERE plus VCE plus ICRC minus VCC. And since you know that IE is approximate, okay, is equals to IC, because we assume that IB is very, very small. So you will get VCE equals to VCC minus IC, RC plus RE. Okay, so basically how to solve this is just similar with the other circuit. Okay, it's just that this circuit is the same, but the step to solve for the voltage and current analysis is the same. Okay, and also you know that VE is equals to IERE, VC for example, VC is over here. I already explained this in the previous video. So if VC, you want to calculate for VC, so VC is from this point to ground. So basically, you know that VC is VCE plus VE. This is VE. Okay, V across RE. Okay, and can be simplified. And if you use KVL, you will get VC equals to VCC minus ICRC. Okay, and this one for VB. So for example, VB is over here. So from this point to ground. Okay, so this one is by using KVL. VB is equals to VCC minus IRRB, but VB is also equals to VBE. So VBE is the voltage over here, which is 0.7 plus VE. Okay, and this is the load line, DC load line for the circuit. So the difference between the emitter bias configuration with the common emitter configuration is that you can see that from the DC load line, this one is the same. Okay, the interception over here is the same. VCE is equals to VCC. However, this one is different. Okay, this one is different from the common emitter configuration. Okay, so the end, based on this equation, the endpoints can be determined from the load line. So to find the VCE cutoff, okay, you know that VCE here is equals to VCC, and at this point, IC is equals to 0. Okay, but for the IC saturation, okay, VCE is of course equals to 0, but the IC now is equals to VCC divided by RC plus RE. Okay, so the difference with the common emitter configuration is that this one you have the additional RE. Okay, you have the RE. For this one, this is common emitter configuration. You don't have the RE. This is common, and this is emitter bias configuration. So you have the additional RE here. The step is the same. So in for the DC load line, you will get the IC saturation equals to VCC divided by RC plus RE. Now let's do the exercise. Okay, for the emitter bias network, determine IB, IC, VCE, VC, VE, VB, VBC. So basically, to solve for this one is, I think it's quite simple because the step is similar to the previous example. Okay, it's just you need to use basic KVL. Okay, so the first question, calculate for IB. So for this IB, like I explained to you before, please use KVL. Show the calculation starts from KVL equation. Okay, so from KVL equation, you can get IB is equals to VCC minus VBE divided by RB plus beta plus 1 multiplied with RE. Okay. For example, if you don't know, if you forgot, get confused on how to derive this from this circuit, please refer back to this. Okay. So this one already been derived in the previous slide. Previous slide. Okay, so you will get 40.1 microampere. For IC, you just use the formula. Okay, IC equals to beta IB, you should get 2.01 milliampere. So for the number C, this is VCE over here. Also use KVL, you should get 13.97. For VC, remember VC, this is the collector feed. So this VC. Okay, so VC is from this point to ground. So you can either use this one using KVL. This one is just from this point. So this is VCE plus IERE. Okay. This one is KVL at this loop. Okay, so VCC minus ICRC. So you should get the same answer, 15.98 volt. Okay, and for VE, so VE, this is the ammeter feed. So this is VE. So VE from this point to ground. Okay, so you know that so previously you know that VC is equals to VCE plus IERE. So you can calculate for VE, which is VC minus VCE. Okay, and VE is equals to, of course, IERE, and IE is equals to IC, because we assume that the base current is very, very small. So you will get 2.01 volt. For VB, VB is over here. So from this point to ground, so VB is equals to VBE plus VE. So this is 2.71 volt. And lastly is VBC. Okay, VBC is equals to VB minus VC, or you can use VBE minus VCE. So this one is another example. Given the emitter, this is the emitter bias configuration circuit and its collector characteristic curve. Okay, so this one is the collector characteristic curve. This one is the circuit. Question 8, draw the load line for the network of figure 26.26a on the characteristic for the transistor appearing. So given this circuit, the question asks you to draw the load line here. Okay, so how to draw the load line? You need to calculate for the intersection. Okay, the intersection for the VCE and also the IC saturation over here. Okay, so you can directly, if you remember, you can directly use the formula. Okay, so you don't need to derive. So 2 points on the characteristics are required to draw the line. The first one is the VCE at 0, and also when the IC at 0. Okay, so this one, when IC at 0, you can determine the VCE. When the VCE is 0 volt, then you can determine the IC saturation. Okay, so when VCE equals to 0, IC is equals to VCC divided by RC plus E. So this one already derived in the previous slide. Okay, so you can refer back. You can just remember this. So this is 5.5 milliampere. When IC is equals to 0 milliamp, VCE is equals to VCC. So the VCC is equals to 18 volt. So the resulting load line appears in figure 4.27, this one. Okay, so you will find the VCE and also the IC saturation, okay, the point, and you just draw the line here. So this is the DC load line. Question number 2, from the characteristic of figure 4.27, we find that the VCE cube is equals to 7.5 and ICQ is equals to 3.3 milliampere. So this is the Q point. Okay, so VCEQ is equals to 7.5 volt and the ICQ is equals to 3.3 milliampere. Okay, and this one, the third question is the DC beta. So by using the formula beta equals to IC divided by IB, then you will get E equals to 220. Okay. Question D, using the beta for the network determined in part C, calculate the required value of RB and suggest a possible standard value. Okay, so this one to get the RB, okay, you just use the KVL, okay, use KVL to solve for IB, and then you can get the RB. So RB equals to 910 kilo ohm. Okay, so the last part is the voltage divider bias. Okay, so this one, the circuit is a little bit different. So you can see that now the circuit connection is like this. You have R1, R2, RC, and RE. So if you this circuit, we call as the voltage divider bias configuration. Okay, and this is the collector characteristic curve for the voltage divider bias. Okay. So the way to solve for this circuit is the same. Okay. So when you draw the circuit, this is the first loop. Okay. This is we use approximate analysis. We assume we approximate IE is equals to VE over RE, and you know that VE is equals to VB minus VBE. VB equals to R2 VCC divided by R1 plus R2, and ICQ. Okay, ICQ point equals to IE. Since ICQ equals to IE, then you can calculate for the VCE at Q point equals to VCC minus ICRC plus RE. Okay, so this one, given the circuit, calculate for the VCE and also IC. Okay, the derivation, no derivation, you can just use the formula over here. No problem, you can just use the formula. So this one, VB, use the formula, you will get 2 volt. Okay. You just use the formula if you don't want to derive here. So, and then VE is equals to VB minus VBE. Okay. VB is over here. Okay. Based on the equation, you know that VB is equals to VB. Here, VB is equals to VE and VBE plus VE. Okay, so that's why you get VE equals to VB minus VBE. VBE is 0.7. And then the IC is equals to IE, and IE equals to VE over RE. You will get 0.867 milliampere. And lastly, you can calculate for the VCE. Okay, so this one using KVL. Okay, just use this one. Okay, you will get 12.03 volt. Okay. So basically, if you, it is easy to, if the question doesn't ask you to like derive, you can, if you remember this, you can just use, okay. But still, you need to know how to get this equation, how to derive. Okay, so for example, if you forgot the formula, then the list is you able to derive. Okay, so as a summary, this one to show you for the base emitter configuration. You can see that at the saturation region, it is forward bias, active region forward bias, cutoff region is reverse bias. For the collector base configuration, saturation is forward bias, active region is reverse bias, and cutoff is reverse bias. And you can calculate for the collector current. This is the formula. So at saturation region, Okay, IC saturation equals to this or this. At active region, IC equals to beta IB. At cutoff region, IC is equals to 0. Okay. This one, IC at saturation region equals to VCC divided by RC. Okay. So that is basically the end of chapter 5. So your final exam will cover from chapter 1 up until this slide, chapter 5. Okay, so if you have any questions, you can ask me later. We will have a discussion. And please do your tutorial and submit your tutorial before we discuss. Okay, so and also we will have a quiz, the quiz 2, which will cover chapter 4, and also I will share with you the assignment that you need to do, okay, in the following week. Okay, week 12. Week 12, yeah. No, week 13. Okay. So that's the end for our lecture today. So we'll meet again in the next online lecture. Okay, so thank you very much.